Design a type-ahead box for a search engine. Hi everyone, we're excited to be here today for another Exponent mock interview with Andreas. Thanks for being here, Andreas. For those of you who don't know, Exponent helps you get your dream tech career via our online courses, peer-to-peer mock interview platform, and interview question database. Check it out at tryexponent.com. So thanks for being here, Andreas. For our viewers, can you give a brief introduction of yourself?
Hey everyone, yeah, my name's Andreas. I'm a software engineer at Modern Health, which is a mental health startup in the Bay Area, and I'm working remotely now currently.
Okay, great.
Cool.
Let's get started. So our question today is design a type-ahead box for a search engine.
Awesome. So right off the bat, I think there's probably a few things to consider. You know, if we're talking about a type-ahead box, are we saying for a search engine, we're assuming it's going to be a high throughput, I guess, like something like Google or like an Amazon search or something like that. Okay, awesome. So in that case, here, I'll go ahead and share my screen so that, and here we go. All right, great. So in that case, we're going to probably have to think about a few factors. So some of these factors included are, you know, having a quick response time. I mean, we're going to be serving a lot of different users from around the world, and we want to make sure also that what we're returning is pretty fast. Another factor could be, you know, relevant or contextual results based on where they're searching from or what the user has searched before. And then finally, you know, the number of results or like some sort of ranking of these results. It would probably be beneficial so that we can return to the user the most, in addition to the most relevant to where they are contextually, also in terms of overall popularity.
Okay.
Does that sound all right to you?
Yeah, that makes sense to me. For quick response time, on what magnitude are we thinking?
Yeah, so often I'm assuming we're probably going to want pretty, like, you know, 5 milliseconds or 50, rather, yeah, maybe 10 milliseconds of like response time. 5 will be great to make sure also we're serving probably millions or if not billions of users, just to be able to be responsive around the world.
And is that like estimated response time also based off of like UI factors?
Yeah, so that'll be also making sure that the user, you know, will have to send the response to the server and then receive it back. And I imagine that will require that amount of time also, just, you know, a bit of loading as we asynchronously would call that.
Right, yeah, and you probably want the type-ahead suggestion before you're typing too much more.
Exactly, yeah. Cool. So I guess from here, maybe we can talk about, rather than going into the structural design of this, I actually want to dive into some of the data structures or algorithm that we want to use to handle this, because I think that's actually really important for this case.
Yeah, that makes sense.
Awesome. Great. So in this case, in terms of the data structure, we're probably going to need to use a tree or a trie rather. And that data structure is, we want to aim for like in big O notation, probably O of L time, where L is equal to the length of the prefix that we're searching. So, and also something that's space optimized. I guess, and on that point, is there a certain amount of results that we want to display to the user?
Maybe sort and return the top 3.
Okay, great. So we'll do the top 3 results. Okay, great. So now that we know that, I'll try to dive into this data structure. And, I'll just say, I guess, maybe an example of, we can list out, we're searching with like a string like D or maybe DO. And we can have a bunch of things stored in the tree already, like commonly searched phrases like dog or doll, don't, dart, dip, dollar, and we'll do Doge for fun, because Dogecoin was pretty popular recently. I don't know if it's still up there. So given these examples, keywords, like we probably want to determine also a ranking in this case based on the frequency that we're searching for these. So we'll want to assign weights to each of these. We could say 9, 11, 21, 1, 5. And these are arbitrary, but just to give a sense of, different weightings. So now that we have these guys, we'll need to construct a tree data structure. In order to do that, I think I can represent it here, but essentially we'd want each of these like D at the top, attached to that, another one, DO, and another one, I'll connect this one as well. Another one here, we have a DA path. And I won't go through the whole thing, but just to illustrate an example, we could, to illustrate an example, we could have the here we go, DOG, and then one more example of Doge.
Okay, so then just to recap then, each ancestor node in this tree points to children that have the same prefix as itself?
Exactly. And we would, another important distinction of this tree is we'll want to identify what are substrings or strings in this tree that are actual results versus just a way of constructing the following strings. We can assign rankings only to the ones that have are a valid result. So dog would have, the number 9 attached to it on the node, and same here for Doge would have, 15 on the node.
Gotcha. Okay.
So I guess going from there, we can start to dive into how would this tree work. Well, it gets actually pretty time consuming. We could assume that, right, if we're searching for DO, we'd probably want to return the top 3 results. In this case, we only would have 2 results so far, but in the full tree, we would have, dollar included with Doge, and as well, it looks like don't. In terms of weightings.
Okay, so
go ahead.
So for each query that's typed in, we return results in the subtree of that node?
Yes, exactly. And so the subtree of the node, I guess it would take, L time, which we defined before as the length of the prefix to be able to search for that first node, which would be the root node of the subtree.
Uh-huh.
But then going from there, we would need to search for the all of the nodes underneath in that subtree, which we could maybe define as, here, I'll go up here. So we have O of L, which we already talked about, but we also need to search for the N nodes underneath DO in the subtree to make sure that we're checking for all of the different rankings to compile them.
Uh-huh.
And then finally, we have another check, which would be actually sorting those. Since we're only doing 3 in this case, we would need to sort for the top 3. So that sort operation though would take k log k time, where k is the number of like different nodes that have rankings that we've found.
Yeah, okay. So since it seems like these subtrees could potentially be very large based off of the huge volume of past search queries that there are, is there a way to make this a little bit more efficient?
Yes, great question. So I think going from here, we could try to use a strategy which is actually pre-computing these rankings at each individual node. So in order to do that, we would still run into, every time we search this O of L, but I think if you agree, I think it would be acceptable to do that. However, we want to maybe make this part more efficient. So let's say at DO, for example, which we were using as our example, then we could store the top 3 results in ranked order with like dollar. Oh, I guess I won't type in here, but in this case, we would have, I'll type right in here. We could have the top 3 results stored at DO of dollar with their number, dollar, don't, and then Doge. Does that seem, I guess, acceptable?
Gotcha. Okay. So you would be pre-computing this when you're first constructing the try based off of past search results then?
Exactly. Yeah. And we could, as we dive into maybe the architecture, can talk a little bit more about, but, high level, we could do something that run a job or some sort of process that would continually update these values as people search through these and update the counts and the trees for each of these.
Yeah, that makes sense to me.
Awesome. So I guess given that we're effectively have O of L time because we're processing this N and K log K ranking ahead of time, do you think now we can go ahead and dive into talking a little bit about what we would look for in architecture design?
Yeah, sure. I'd love to see that.
Great. So from here, we're probably going to want an actual architectural piece to be able to represent this try in our backend. So in this case, we're going to go with something, we're going to go with a prefix hash table. I think that would probably suffice, where we have the table would be represented. Here, I'll type it in here. Table could be represented by the prefix strings would be 1 column, and then the other column we can have that array that we've talked about here for each of the prefix strings.
Okay, gotcha.
Okay. And those are would be the top 3 suggestions. And that'll give us constant time as well. Given our prefix string, we could just use that as a key to find the top 3 in that hash table.
Okay, yeah, that seems pretty efficient to me.
Awesome. Okay, great. So now maybe we can talk a little bit about what the service itself will look like, how we want to actually receive all of this and process it. So we're probably going to need an API server here to be able to receive and send requests. Let's see, and send responses rather. And to here, oops, I don't need that. There we go. And we're also going to need to have some sort of DB or Redis cache that's storing all of these values that we pre-computed in this table. So, okay, that's pretty high level, but now we talked about before, we definitely need, oh, there we go. We definitely need that response time. We're serving to millions or billions of users. How can we make sure to prioritize that? So, and be able to scale to that volume. Well, in order to do that, we have a few ways of doing it. We can create more API servers. So right here, and parallelize those and make those horizontally distributed.
Gotcha. Okay.
I guess also in that case, we'll need a load balancer to distribute the load between them. So right here in front of these. And is there a particular way of distributing load do you think will work in this case, or would it be fine just to do a standard like round robin load distribution?
Well, I think that might be more dependent upon the use case of this particular system. So something to keep in mind is that it's a very, it's meant to be a very scalable system that can handle high amounts of throughput with very little latency.
Definitely. So, okay, that's a good point. Maybe we would then need to distribute by load on each server and like do a, lowest capacity server redistribute load to that one.
Yeah, that makes a lot of sense.
Awesome. So then given that, now we have multiple API servers to service requests and a load balancer distributing load between them. Let's maybe talk about the DB to also be able to make sure we don't have the one single point of failure. With this one DB, we could, if it went down, then we'd go down completely. So we probably don't want that to happen. So given that, we'll have these multiple, we'll have multiple of these API servers going to multiple replicated DBs. I guess we could go with a Redis cache or DB. I think if we go the DB route, I would probably use something like a NoSQL database that could, be able to have pretty fast response times, like maybe like Cassandra or other types of DBs. Awesome. But if we went the other route, then could definitely use like a bunch of Redis caches or memcached. I think either way would work in this case.
Yeah, so it makes sense that those NoSQL databases would be more efficient, but are there any drawbacks then to using that instead of a relational database?
Yeah, I mean, so in this case, it's pretty simple out of the box, but longer term, NoSQL, I think, does have less, if I recall correctly, it's consistency versus it has more availability and like less consistency. So since we're having it, we could run into issues with that, where we would be highly available, like, you know, really low latency, which is great. But yeah, if we wanted to, we could go down the route of a relational database, and then, you know, do some sort of sharding or like set it up where we could have a distributed database as well. Just it would be a bit more complex, I guess.
Yeah, okay, I see.
Let's see. Yeah, I think this is probably how I'd go about it. I don't know if I'd, how does this all look to you? Is there anything else you'd like to talk about maybe, or go into further?
Let me think about it. Okay, so for the algorithm right now, as it stands, you're using your try to store the most frequently searched searches, right?
Yes.
So what would happen if you maybe wanted to personalize your search results according to what a specific user has searched before, or maybe the location that they're in?
Yeah, that's a great point. Thanks for calling back to that, because I did, I guess, mention that in the beginning, but that would make it even more relevant or contextual, is being able to allow a user to search based off of their, you know, individual search history. I think we could make a more personalized search experience. Overall, right now, we're, yeah, of course, ranking globally, but an individual user, we could incorporate their search history of keywords, create a prefix hash table as well that for each user incorporates all of their searches. And additionally, I think in terms of to your point of location, we could have some sort of real-time or trending results based off of the user's location. And that, you know, could be, let's say, 1,000 keywords per day. We search for the prefix in that table and incorporate the results. And so we'd probably have to run some sort of like 3 different queries to these 3 different prefix hash tables, and then, yeah, combine those results in some way.
Okay, yeah, so then you would get 3 sets of Typeahead suggestions. And then would you like just like rank them together, or like find the intersect? What do you think would be?
Yeah, that's a good point. I think in either we could go the route of intersect. If we didn't find that, maybe we could spend more additional time and come up with like a weighting system of how we wanted to weight the user's searches versus the broad searches versus the highly real-time or trending results. And I think coming out with some sort of score to then rank and standardize all of those results would give us a top 3 results we could provide from across all those 3.
Gotcha. Okay, yeah, that makes a lot of sense to me.
Awesome.
Okay, so I think this is a great place to stop. You did a fantastic job. Thanks so much.
Awesome, thanks.
So I think it's good for us to debrief now. So how do you think that went? What do you think went well? And what do you think you would want to improve more?
Yeah, so I think, you know, actually thinking back to how I started, I could have even broken down more my process of how I was going to step through the entire system of saying, you know, let me start with A, and then I'm going to move on to B, go to C, and then end up at D. I kind of dove into some of the higher. I'm glad I didn't fall into the trap of like going right into the architecture design, but I could tell that would have been good as well to add. But I think otherwise, I felt pretty comfortable with this question. But yeah.
Okay, great. Yeah, that's a lot of good feedback. I agree that structure generally helps a lot in system design questions. But you had a lot of good structure actually, and I wanted to call out specifically that I really like that throughout your entire solution, you always made sure not just to explain your like what elements were in your solution, but why you designed it that way. So you explained like the efficiency concerns and also like the user perspective as well. And you also explained a little bit about like the trade-offs of like consistency versus availability when we were talking about databases, for example. And that's all really excellent. And it demonstrates to your interviewer just how much knowledge that you have about system design. So that was awesome. Some things that might have helped make your solution even better is that, so we talked a little bit about structure, right? So sometimes what helps actually is asking even more clarifying questions in the beginning of the interview, because that helps your interviewer help you scope out the question. And that's what they're trained to do. And also you had a list of factors, but it would have also helped to maybe flesh that out into an explicit list of like requirements, you know.
Great, that's a great point.
And then the very last thing was, so I think you made brief mention of this, but then it didn't quite go into it, was we talked briefly about how for building the try itself, you want to have some sort of offline system that like builds it like asynchronously. So it doesn't need to run as fast as the actual like API Typeahead service itself. But it would have been good to discuss like, how do you determine how often that service should run, you know, and how much of the actual search data should it consume? Should it sample only the most frequently searched queries? And is there a reason why you might do that? Like you might want to only take the most frequent ones because of privacy concerns, for example. And maybe in this particular aspect of the design, having the most up to date search results is not maybe as important, you know.
Definitely, yeah, I think that's a great point, and I would have loved to like dive into this. Those are really good.
yeah, it's definitely a really interesting aspect of the problem. But otherwise, cool. Fantastic job.
Awesome,
so,
thanks.
Thanks so much for joining us today, Andreas. For those of you watching at home, good luck on your upcoming interviews. Bye.
Thanks so much for watching. Don't forget to hit the like and subscribe buttons below to let us know that this video was valuable for you. And of course, check out hundreds more videos just like this at tryexponent.com. Thanks for watching and good luck on your upcoming interview.